Alright, so we have seen that in complex circuits we either have three elements of interest. We have resistor, right? We have a inductor, right? And then we have a capacitor, right? And then we've already discussed what each and every one of these does, right? We said that for the resistor, it only consumes real power, right? Which we represent to be P, right? And then for the inductor, it only consume the reactive power, which we represent that as Q, right? And except for the capacitor, it does not consume any of them, but either reduces the supply. It either supplies the reactive power or it reduces the consumption of the inductor of the consumption of the reactive power by the inductor, right? And then we said that when we have a system that has these two, right, in it, we end up getting something, and these are vectors to be clear. These are vectors. We end up having a combination of this, and then we have what we call a apparent power, right, which is S. That means the apparent power, we have a real power component, and then we have a within the apparent power, meaning that we have a real power component, and then we have a reactive power component, right? I'm just writing, this is not how we write it, but I'm just showing. So let me do this way, right? Yeah. So at times it becomes a bit complex in circuit when we try to write them directly, right? And we start the same apparent power when we have the RMS values, right? We can find it directly when we have the RMS values. So we can write it this way. Let's see. We have a I RMS times V RMS, and this will give us what apparent power, right? But then in some circuit it becomes complex in a way that when you get everything in the RMS value, the computation is a bit not clear, right? So we found a way to do it still using the complex numbers, right? And then in our discussion so far, we've seen that when we do the Cartesian system, when we were trying to do the complex number system, it's something like this, as we've drawn, as we can see in this one, it's something similar, right? It's like this. Let's see. We have the road part here, right? And then we have the complex part at the side, where here is where we have G minus 1. Here is a G, and here is a minus G, right? And here is a real part, right? All right. So the same applies here. It can mean that we have our power here. If you are trying to represent this whole apparent power, right, you can still use this too, right, by using the complex form. So we know that we end up getting the apparent power in this form where we have S, right, and we have some quantity for the real power. Let's see A. Let's see something else. Let's see Q. Okay, W, right, for the real part, which will be this side, right, and the apparent part from the combination of whatever we have here, depending on what we have, it could be plus or minus, right? So plus or minus, and we have let's say V, right? And then because of this J here, we have to introduce something to show that's a complex part. So we have a J. Let me use another color. So G. So most of the times it's written and just before the other value, just to know that we are doing it in complex form, right? Yeah. So that will mean that if we are trying to find the same power using something of this sort, we won't have to use the current in RMS, right? You won't have to use the voltage in RMS. So we have to get them in complex form, right? And if we say the complex form, they always write them, right? This is one way. This is basically the rectangular form, right? And we also have, so let's see if it's voltage, right? So now let's go with this. If it's voltage, we have it in this form where we have just the RMS value, right? And then we have the phase shift, right? Let's see this, right? This same one can be written this way, where we have the RMS value, right? And then we have cos phase shift. Let's make it small so you can see what we're doing. Let's bring it down. So this same voltage can be written this way. We have V RMS, right? Inside, and we have, because of this phase shift here, we have cos phase angle, and we have plus, this is another way of writing the rectangular form, right? J, let me use another color. The J is very important. So we must bring it before the what we want to write so that we always remember it, or we might forget it. And then we have sine and the same angle, right? And now you know, meaning that we can still write the same voltage in this way. We have A, right? And then we have the J, and then we have the B, right? This will mean that if you have a voltage, right, this will mean that there's the real part of the voltage is the complex part of the voltage. That's what I'm saying, right? So now we are still talking about power, though, but we're trying to find a very important relation, right? So the same will happen for the current. This we have current of this sort. That's when we have IRMS. Let's say the phase angle for this one is beta, right? That means that we have IRMS. So we have cos beta plus J, very important, the complex notation. And then we have sine beta again. Right? This will mean that we can represent it this way. Let's let you see, right? Complex notation, very important. And then we have D, right? Because we're talking about power in complex form, you have to make sure that the voltage and current are in complex form as well. And then we've seen clearly that if you are doing computation, the calculator can help us do things when we have everything in this form. If I can do all of this, but the ones that can punch in directly are these ones. Easier to punch in are these, right? And we've seen that. But currently here, what we'll be doing is we'll be working with the last one, right? The last notation, which is this form. This one right here, right? Okay. Okay. So yeah. So meaning that if you are trying to find the power, sorry, the apparent power, right? S, it will be of this form. What we have an A plus, might be in right, right? Times, let's put the G here, and I'll have a C plus this, right? Meaning that if you're trying to find the apparent power, this is how it should be, right? Okay, so now let's go ahead and do this multiplication and see what comes out. This representation this relationship that I'm trying to show here is very, very important, right? So in fact, you might not even need to prove it, but then if you go through this process, you get to understand why we do it that way, right? So that will mean that we have let's see. Okay, so now we are using the A. We're just expand, that's all. Just expand. So let's do that one first. So now we have A, C, right? And then we have plus A dot, we have a D, right? And then we have D, this one part. So now we are done with that. Let's see. So now we are doing this and the whole of this, right? So that means that we have J. Let's put the plus, there's a plus. That means that we have a J, right? And then we have B, right? And it's multiplying what first? C, so dot C. But we have another plus again, right? And then we have okay, this will mean we have J, and then we have B multiplying J, and then we have what? D, right? Okay, so now let's see what's happening. Okay. So we finish with this. Okay, let's pay close attention. The ones that we can see, there are 4 real numbers, like for the real number part of the complex number is this one right here. Right, so let's write that first, because we are going by this notation where we have just the real part. We have the real part plus the complex part, right? So that's the general way we are writing it down. So that means we have A and then C, right? Is there any other one that we can directly see that is just a real part? We can't see for this, we can't see for this. But then let's pay attention to this side. Something that we must look here. We know that this J that we see here, this J is equal to square root of -1, and we use J because we are doing what do you call it, electricity here. We have current, and then for the sinusoidal quantity for current, we can have I, right, which is something like this. But mathematically, this is the one that is used a lot. But if you don't see this and CJ is the same, but because of the current that we use, that's why we don't use I, but we use J, just to make sure that it's not current you're talking about, but the complex notation, right? Okay. Then we know that this is this, right? So let's look at this very well, meaning that there's something we can do to this to make it just a real part. Alright, so let's look at it. That will mean that it's a square root of -1. This J here, square root of -1 squared, right? So this J times J is square root of -1 square root of -1 squared, meaning that we end up getting what, just -1, right? So that's what happened there, meaning that this just gives us -1, so you have a negative here, and B and D gives us what, BD, right? Yeah, and then we end up getting this. We can bring the J out. Now we're trying to simplify, right? So we get a J here, right? Here will be plus, and because it's a real part, we can put this in brackets. We have a J here, and then what do we have? We're talking about these two now, this and then this, the ones with J's, right? Okay, so that will mean that we have a bracket here, we have AD, right, plus or BC, and this is what we'll have when we are trying to find current. Sorry, I'm trying to find the apparent power when we have the voltage and the current, right, as we've seen. But then there's something that we are missing here. Okay. The only issue with this is that we won't be able to see directly. We won't be able to see directly which part of this is the real power, which part of this is the apparent power, and we can see clearly that whatever that is inside here is the real power. Whatever that is inside here is the reactive power. We can't see that, right? Okay. So meaning that there's a flaw with this particular way of doing it. So what has been done and what they have seen so far is that if we write the power this way, especially if we are doing using the complex forms, whenever we are finding power and we have the voltage, in complex number, we have the current in complex number, it helps and it makes our work easier when we do it this way. So that you see this representation somewhere, V, and then we have I, and there's an asterisk here, right? What it means is that we find the conjugate of the I. The conjugate means that we just change the sign in the middle. Right? So instead of doing what we have, where is it? A minute. Let me clean this up and use it, so we see what we're actually doing. Okay. Then again, this part is just the explanatory part. We just want to see what's actually happening using a complex number, so we understand why we do what we do. Okay. All right. So instead of using this part that when we multiply everything, it gives us this, that we don't know clearly which part is the real part, which part is the reactive power, right? There's a way that there's something that they've seen. They've seen that if we are doing it in complex form, we do it this way. Instead of writing it like this, you write it in a very similar but something different, slightly changed. So you see V, you see I, you see a star here. This star here, let me just use a different part. This star here is saying that this star here is saying that the current here in the complex number form has to be conjugated, right? In order for us to see clearly the real power part and the reactive power part, right? So that will mean that instead of doing it this way, when you see this representation, right? A minute. Okay. Meaning that when you see this representation, it's a slightly different, but that's how it comes. To show us this is how we actually compute it. The same thing, but the current is what, because this star here is on the current is what, conjugated, and that's how we write it. We change this here to negative, Let me highlight it in color. So whenever you're trying to find the apparent power and then the voltage and the current are in the complex form already, you actually have to conjugate the current. So that's what this star here is doing. Just trying to see that this current here is conjugated to this form, right? So now let's try and multiply this and see. You see that clearly we get to get the real power aspect and the reactive power aspect, right? So let's see. So now we are doing with the A with this, right? So we have a AC, right? And then we have minus A dot J D, right? And the other one that we have when we're using with the JB is we have a plus here, and then we have a J, and then we have a B multiplying C, right? And then we have the minus comes, right? Right, and then we have the J, right? And then we are using the minus now. Yeah, J, B, right? Multiplying. So we've done for the A, now with the JB, JB and C, JB, and then J, D, right? Okay, J, D. We've expanded. Now we are simplifying, right? So we end up getting. So let's see the row parts that we have. You know clearly that the ones that will be just row parts is this, right? And what again? The ones that have JJ, this and this. Right? So let's see. So we have AC, right? And then when we multiply these two, we get a negative, right? And then let's see. Let's talk about this. There's a negative there already. Let's do it this way. Okay. So then we have AC here, right? And then this negative is what we bring here. But then when we multiply this JJ, we get a -1 as we saw. So that makes a negative that become positive here. Right? So here's positive now. Okay. And now we end up getting a B and D. So this will mean that this is all we have for the real part. Right? And then now we are working on these two. That will mean that we have we bring the J out. J. Let's just make it a positive, right? And then bring a bracket for this particular one here, right? The A will be what? Negative. The AD will be negative, so we get AD, right? And then here we get a plus, and we get BC, which all of this can be rewritten to this form. We have AC plus BD, right? We get the J later, BC minus AD. So this will be the whole representation. Let's remember our G, then our plus, right? And the difference between this, between what we just found, this one right here, which we found by multiplying these two, that's a conjugate one, and then this one right here, which we find by without conjugating, is that we get to see that let's see, this side is a plus and there's a reason, right? And this side ends up being a negative, right? Okay. And we know clearly that when we are doing the representation, let's go to the diagram. See clearly that real power can only be positive. It can either be negative or cannot be negative. It cannot be negative. So you see that real power is only here, right? Real power is only here, always positive. But then we know Q can be positive or negative dependent, right? So Q is positive. When it's positive here, it means that current lags. This means that current lags, or let's see, there's something else we say, power lags when Q is here. But when Q is down, right, we have something like a negative Q. We end up saying that current leads. So whenever you see that, this is what it means, or power leads, right? Yeah, but P is always positive, right? So that's why this representation is not favorable. This one, this here, is not favorable, right? That's why we do the conjugate this, and we have this. We have get a minus here, and then we end up getting this form, which is the accepted one, right? So always, whenever you have power, you conjugate. You are trying to find power using the complex forms, and then you have the voltage and current. You conjugate the current, right? Conjugate the current. Very important. Conjugate this, right? This all will turn our power. Sorry, our apparent power. Very important. Apparent power. This all will turn our apparent power, which is the S, to this form, where we have power, right? We have a plus or minus, depending. So plus or minus. We have our J, and then we have our Q, right? Where this is power, and this is the reactive power, right? So this will be the final representation that we have, right?